All right. I'm gonna need it over here.
Yeah, you're good. You're good right now.
What do we? Go ahead. Who's got the question? Which one was it again?
Number 2. 11.9.
Suppose you know that the series. So we know that this series, number 2, 11.9. We know that this series converges for x less than 2. What can you say about this series? Oh, x to the n plus 1. Oh, okay, okay.
And the first series is Bn, Xn, X to the
Excellent.
n.
Thank you. That makes more sense.
So, the second one is just smaller, so it converges harder.
That's what I wanted to say.
Have you tried just applying ratio test to this?
You just do like
Yeah, what would the ratio test look like for this?
xn plus 2.
But what?
So it'd be, what's that?
Sorry, what is the question? Is the question asking us to find the interval of convergence for that one?
It's saying what can you say about this, which is sort of implying what can you say about the interval of convergence for this.
Okay, that's
Yeah. That's the only thing that they told us, so they kind of want to ask you, what can you say about this?
because I didn't know what that one was asking either. I thought it was just it converges.
Yeah, the way they word it, you could just say, oh, there's more stuff in it. And then go to the next one. There, I said something about it. But they're implying, what can you say about the radius of convergence?
It would stay exactly the same because n is still going to infinity, even if you add 1 to it, right?
There's an extra piece. Right? I don't know. So have you tried it yet?
So we should do ratio.
What would it look like for ratio test? Everything would have just an n plus 1, right?
Yeah.
So it'd be b n plus 1,
X.
x to the n plus 2 over n plus 2 times x to the n, or n plus 1. Right?
So would that e of n act like a exponent then? Like if you cancel it with the one on the bottom and say you have 1 b left? No.
That seems right.
Oh, no. So, like, when n is 0, this is b0, which is I have no idea.
Right.
It's not a power, it's a subscript meaning it's just like Cn, C sub n.
Yeah.
They could all be 1. They could be, anything.
If we know b of n, if we knew b of n converge though, like the ratio of b of n plus 1 over b of n would just be 1, right?
Well, if you know that this converges for this,
Yeah.
right? All right, so you're thinking the right way now. It sounds like nobody else has done this yet. So that might be all I'm gonna say, because you're the one that asked the question. Okay. So this is number 2, 11.9. They ask you, they give you this, and they ask you, what can you say about this? Adam's got a good point. I could say a lot of things about this, but they imply, what can you say about the interval of convergence for this? Right, so you just start to try to do ratio test.
Right.
And you can use this information to help you. Yeah, okay.
If could we say that b of n converges if the top thing converges? The b of n next to them?
Oh,
Are we allowed to say that?
okay. What's it, if I did ratio test for this guy, right?
Yeah.
Okay. You basically said it, so I'm not sure, okay. So the ratio test for this guy, right, would be b n plus 1, x to the n plus 1 over b n x to the n, right?
Yeah.
Absolute value. So you get b n plus 1 over b n times x. And you know that this leads to this,
Yeah.
so you pretty much know what this limit has to be.
Yeah, it's gotta be 1. Or it's,
If it's 1, you sure? Would it lead to this?
oh.
Oh, okay.
You're right.
Anybody else paying attention? did more than I wanted to, that's okay. I thought you had it, because of what you said earlier, but now you got it. Okay. That's number 2. Section 11.9. Very good. Anything else from homework stuff? Yes?
Did you show how we would start one that uses, the give to integrate kind of?
Oh, yeah, good. Yeah,
15.
we have several kinds of problems we should do more examples of. So what are you looking at?
I was looking at 15 and 11.9. F of x
Oh.
equals L and 5 minus x. I don't know if it's a sign, but
Let's see. Okay, so already got what they want for this. Yay. Try to leave that up there for a moment. Yeah, because this section, remind me, all we know is 1 over 1 minus x, right?
Yeah.
I like it. So real quick, just to kind of build up to this. 1 over 1 minus x is 1 plus x squared plus blah, 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 is the sum. And that's only converges for what? Yeah, because that's basically just geometric. We just made it look like a function of x instead of some sequence that we kind of added the sums, the terms of. So what if it was this?
You need to get rid of that 5.
pull out 5.
Yeah, if you do this, right? Now here's where we really didn't do a lot of this. We sort of talked about it like on the periphery. If I know that 1 over 1 minus something is 1 plus something squared equals sum of something to the n, blah, blah, blah. Well, what's the something now?
X over 5.
Yeah, so I can just put an x over 5 here. No.
Would it be bad to leave the 1/5 inside, like as your A?
Oh, that's not bad. Leave it inside, put it outside. Sure. So everybody get what I just did. These are just functions. They are functions. If I plug something in here, if this is equal to it, I would just plug that here also. If I wanted to put a 0.2 here, I would put a 0.2 there. Well, we have an x over 5, so I'm going to put an x over 5. That's how functions work. Whatever I put into them, I put into them. Yes?
Why wouldn't it be a negative x over 5?
I don't. Because if it was a plus x,
No, I'm talking about in there.
no. Are you cool with this?
Yeah.
Okay. That is in 1 minus x. So 1 minus stuff is 1 plus stuff squared is sum of stuff to the end.
Okay.
So this is 1 minus, so if this would have been plus, then you would have been right.
Yeah, okay, yeah. But because
So let's do
that
that
is
real
equal
quick.
to something plus, yeah, because it's plus,
What if I had this?
then it's 1.
2 steps, 2 things I have to do.
Divided by 2?
Well, I have to take out a
Yeah, constant.
1/2, right?
Mhm.
Well, you can't take out a 1/2. No, don't take out a 1/2. All you have to do, one thing, I'm sorry, is you have to make this 1 minus stuff, right? The important thing is this 1 here. So this is 1 minus
Negative 2x.
negative 2x. Now you could do.
Yeah, okay.
So I know 1 over 1 minus function of x, stuff. I know what it does. So if I can identify 1 over 1 minus stuff, I can just put this where x is. So this would be
Yeah.
1 minus 2x plus 4x squared, right? And then what would this look like? It would be the sum n equals 0 to infinity, negative 2x
To the end.
to the n, which I can write as negative 1 to the n, 2 to the n, x to the n, if I wanted to. Crazy. Okay, maybe. So now we're finally building up. So now we can add some extra shit on top. What's the one you're talking about? Natural log of
X minus 5.
x minus
Or
5.
no, sorry, 5 minus x.
5 minus x. Okay.
And we want to Find a power series representation and determine the radius of the curve.
Yes. Okay, so, I do know the power series for the derivative of this, correct?
Right.
Yeah. What is the derivative of this?
1 over 5 minus 6.
Yeah, 1 over 5 minus x, and that's, well, negative 1 over 5 minus x,
Yeah.
right? So it would just be negative what we did up here, is that cool? Okay, and then, so that is what this is. We already did the work up here. Where'd it go? What would I do to this then to get the x, to get what this is? What do I have to do to this side to make it become this? Integrate it, so I better integrate this side and see what that is. That's the beautiful thing about these power series. If you have a function and you know what its power series representation is, and you change the input, you just change the input in the series. That's kind of beautiful. If you know this and you want to know something about a derivative or an integral of it, you just take what this is and you take the derivative, or you take the integral, whatever you need. So this is a question about an integral of a thing that I know. Well, it's a little bit turned around, right? So we had to first take the 1/5 out. There's also a negative that I have to throw in there. No worries. Maybe? Yes?
Why do we have a negative one? Is that just the derivative of natural log? Or?
Well, the integral of natural log, I'm sorry, the derivative would be 1 over 5 minus x times the derivative of this. Chain rule, yeah, chain. Okay. So I want to do more of that. I want to do more of that. This is one reason why, hopefully everybody got their email. Is there anybody upset that I pushed the test back by a day?
No.
Okay. Anybody upset that I'm going to give you the whole Thanksgiving week off?
Nope.
Did everybody?
I'm extremely
I dislike my
angry.
family.
Okay. You're gonna have to
I had to spend time.
push that anger down. Just push it down, make it into a little ball in the pit. It won't do anything to you. It'll be. Okay.
I don't have to stay till 8.
So we have time now to do a few more examples of what we just did, right? Because we really didn't mess with this stuff much. We didn't mess with it enough. We need to play with it some more. But does that make sense? Okay. Yes.
Can we go on with the integration of that?
Sure. What's the integral of this?
X squared over 10.
No. Okay. Let's do a couple things.
Oh,
Okay.
never mind.
Right? It's the same thing, correct? So what's the integral of that? Well, the negative 1/5 just comes to the right. The sum we'll worry about in a minute. What's the integral of x? Well, what's the integral? What does this do? Isn't 1 over that just a constant?
Yeah.
So it just comes to the right. Just comes along for the right. What's the integral of x to the n? That's just the definition of
X to the n minus 1 over n.
you,
I mean n plus 1. Sorry.
x to the n plus 1 divided by
n plus 1. Yeah.
Okay. Crazy.
Yep.
How would you, couldn't you develop, now that we know Taylor series, couldn't you do the steps to figure out the Taylor series for this and show that it is this? Right, now what's the, does anything have to change about this? No, it's only when you do derivatives. This will still be 0 to infinity.
Oh, wait, can you say that again?
Say what again?
N changes from 0 to 1 when you do a derivative?
Yes, we'll do another example.
Wait,
of that.
so the bottom one should have been a
Oh, that
1?
makes sense.
Or no?
No, it's 0, it's fine. Yeah, I think,
Yeah.
where did I go? No, this is just looking at the series.
Oh,
Yeah.
okay, I see. So
We
that's
didn't
like
actually take
that's
a
like the
derivative.
standard right there.
We took a derivative of the function and then I wrote a series for it. I didn't take a derivative of any series. Okay. Let me just calm down. It's gonna be okay. I want to reclaim some of my board. So let me just do this next thing real quick, and then we'll do more examples of this. Okay. In fact, we'll do a little bit more with this. I'm gonna leave this here. Yes.
Quick question.
Yes.
When you're talking about taking the derivative and like switching the n to 1, keeping the n at 0, does that effectively change anything? Because doesn't the first term?
It can.
Okay.
So that's why you have to be careful and actually think about it. That's why I left it alone when we did it, just to make sure if anything weird happened, But no, so, but especially when you take derivatives, you have to be a little careful.
Yeah.
There was a situation last time we did where you had to change it because it made something not even exist, that didn't even exist show up.
Like natural language.
We'll do another example.
But you can re-index it just by adding 1 to the ends, right? But you can't get it back to n equals 0, you just have to index it.
Oh, sure you can, of course. Yeah. We'll do a little bit of that too. Yeah. I didn't, I gave out some of these quizzes earlier, so let me give out the rest of these. Let's see. Was it Debian? Yeah.
You got the pre-release.
Math. Jacob. Jordan.
I forgot to bring my sunglasses.
Nice.
Here.
The
Do you have the practice exams too?
yes.
Patrick.
Okay, all right. So let me do something real quick so I can reclaim some board space. Just want to show you something real quick. What is happening here? Here's e to the x. So we can develop. I don't think we did this together, did we? We didn't develop the Taylor series for e to the x. We can do that. But here's the Taylor series for e to the x. Which means, what we just said over here about if I have a function and I throw something else into it, what do? It's kind of funny the way I say this. If you throw something into a function, well, you throw it into the function. Okay, Jeff, good job. You're a Yogi Berra, right? If anybody knows Yogi Berra. So e to the ix, I just throw an ix wherever I see x, yes? What is I squared? -1. And then x squared is x squared. What is I cubed? -I, right? And real quick, I don't think, did we talk about complex numbers at all? Anybody know what a complex number is?
Oh, yeah, I get it.
What's up, sorry?
So it's a very sophisticated number.
It's like. Oh, wow.
Yeah, it's basically on the z coordinate
It's
of
the
what
z.
Alright, so let's not overthink it. If I multiply by -1, that is a 180 degree turn. What do I mean by that? If I multiply 1 by -1, don't I turn here? Okay. If I multiply -1 by 1, don't I come back here? So that is the very boring -1 to the end is -1, 1, -1, 1, -1, 1, -1, 1 forever, right? Okay. In exactly the same way. So if I can turn 180 degrees, I should be able to turn 90 degrees. What happens then? Well, I multiply by, so if this represents multiplication by a full -1, 90 degree term should be multiplication by a half of a -1. So watch this. This is so freaking cool. And we just give this the letter I just to make it easier to look at, right? Much the same way we give 3.1415 blah 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 blah. We call it pi. And E and all that stuff. You guys kind of with me so far? The idea is that yes.
Why is half of -1 not -1?
Because this is multiplication, right? So if I multiply by -1 to go 180 degree turn, I'm going to multiply by half of -1. Well, when I'm talking about multiplication, how do I take half of something? What is half of 9 multiplicatively? What is half of 9 multiplicatively? 3. Square root of 9. Yes? Half of 9 additively.
81.
Half of 9 additively.
It'd be 4.5.
4.5. Yes? since I'm talking about multiplication, when I say half, I want to go halfway, I multiply by half of what I just did. Square root of it is what I mean. Okay, I like it. I knew I should have brought something with capital.
Is this 1110 or 11.9 still?
This is nothing. This is just complex numbers right now. Now, I mean, this is just so freaking cool. So did I show you that picture I probably didn't show you the video about complex numbers. Shoot, I keep doing this. I might post it on Canvas. It's freaking cool as shit. Every time we graph something, there's a complex, just like there's a y-axis coming off the x-axis, basically every point of x, there's like a y. For every point of x, isn't there an infinite number of y's going up and down?
Yeah.
There's also an infinite number of imaginary numbers going out and in for each axis. So when you have ever graphed a function like this, you have graphed a slice of it in 2 dimensions. In reality, it's a 4-dimensional thing. What the shit? All right, sorry. So maybe, I should sneak that video in because it's so freaking cool.
So
Yes.
isn't what you described just like the Z, like the depth?
Say
Or is
again?
I different from Z?
I is different from Z. Z is like a physical 3-dimensional thing.
Yeah.
I need you to understand. Not only is it coming off the x-axis, it's also coming off the y-axis.
Oh.
And they all have to be perpendicular, so that needs 4 dimensions, right? Everybody, chill. It's okay. It's okay. We're not going to suddenly start drawing 4 dimensions. Our minds are going to blow, and all of our everything's going to go white. Yeah. No, it's going to be okay. It's going to be okay. Let's come back to this. This is 1 dimension. This is just an x-axis, and this is the imaginary part coming off of it. The word imaginary should have been lateral. I agree with that. We should have called them lateral numbers because they are to the side of any axis of real numbers, right? When negatives were invented, we called them imaginary. People didn't think they existed. If I have 3 apples and you take 4, I have negative apples. They're like, what are you talking about? What the hell's a negative apple? Little apple black hole. Right? So of course, but we all know negative numbers exist, right? When I was a grad student, you just had to take a look at my freaking bank account. Existed a little too much for me, right? So, this is such a cool. I didn't learn this till later. I was taught complex numbers such a boring ass way, and later I learned this is what it really is. A full, well not a full, but a half turn is multiplied by -1. So half of that, a quarter turn, is multiplied by half a -1. Multiplicative. Now watch this. So what I have then is this is 1. This is I. So I multiplied by I. If I multiply by I again, it's got to be -1. Because I know if I do 2 90-degree turns, it's the same thing as a full 180. It's got to be -1. We know that. And sure enough, what's the square root of -1 times the square root of -1? Negative freaking 1. So I squared is -1. If I multiply by I again, what's -1 times I?
Negative I.
Negative I, which look at this axis makes sense, right? I goes this way, negative I goes that way. And of course there's 2I, and there's 3I, and blah, 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 blah. And then if I multiply by I again, negative I times I, it's negative I squared. It's -1 times -1 is 1. Comes back. Okay. And that's why I to the 0 is 1, I to the first is I squared is -1, I cubed is I to the 4th is 1, and then it repeats. So -1 goes -1, 1, -1, 1. I goes, well, if we start at I, -1, negative I, 1. I, -1, negative I, 1. Bam, forever. Maybe? Because -1 is half a turn, it's done. I is quarter of a turn, quarter of a turn, quarter of a turn, quarter of a turn. Now I start over again. Yes? Yeah, it's a lot more than I thought I'd talk about, but that's okay. I don't know. Does that help at all with complex numbers? Okay. So, do you see how there's inherently rotation when you think about complex numbers. There is inherently rotation. So then you can start thinking, well, what's a 30-degree turn, Jeff? What would that be? Jeff? What's a freaking 347-degree turn? What's that? Jeff?
Wouldn't you
I don't know.
do?
I'm not gonna teach you, that's not part of what I teach.
Oh.
Just of course, anyway.
But it is a thing.
Wouldn't you start introducing trig at that point, because you can take
Yes, so you start using trig, and you start doing what we're about to do right now. This should be old news, part of this should be old news, actually, I don't know, depends on who you had for pre-calc. Alright, so here's e to the x, here's e to the ix, so I just threw an ix in and they get this. Then I simplified it a little bit. See, you have the purple, I kind of put them aside, 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial. Then the green, they will all have i's in them. So, if this sounds painful, I pull an I out, and I get x minus x cubed over 3 factorial. If you look this up, this is cosine. And this is the one we did create, Taylor polynomial for, that's sine. So e to the ix is equal to cosine x plus I sine x. And I don't know, did any of you, does this sound familiar, taking a complex number and writing it in terms of r and theta?
No.
No? Shoot. See, it depends on your pre-calc, or it depends on your memory also. Right, because sometimes this gets really crunched at the end of the class. But basically, so now watch this. So that's, I really want you to see this. I wrote e to the ix, I noticed the purple dudes were this and the green dudes were that. So e to the ix equals cosine x plus I sine x. That's what it is. They equal each other. There's no way in hell we would know this if I didn't look at it in terms of their Taylor polynomials or Taylor series, right? Nifty. Now, just to complete this, what if I put a pi in there? Is that cosine pi plus I sine pi? What is cosine pi? What's sine pi? 0.
Yeah.
Right? So don't you get e to the I pi plus 1 equals 0? If I would have thought about it, I would have worn my shirt, but too bad.
Wait.
Ooh, you're
I dozed off for 2 seconds and now my brain just exploded.
That,
Too bad.
the Euler's formula.
But real quick, last thing I'll say about this, I'm really sorry, this is not something that we're gonna do, but it's something you can immediately see once you have Taylor series. Do you start to understand, when you learn something new in mathematics, I always get students that are like, well, what the hell can I do with this? And I love the students that are like, how does it help me buy lettuce? I'm like, I don't know, man. I actually had somebody literally ask me that. How does that help me buy lettuce? I'm like, how does anything help you buy lettuce? So what are you talking about? How does playing guitar help you buy lettuce? Be quiet. So, earn money, shut up. So, these Taylor polynomials helped us determine this relationship. And then you're like, well, what good is that? Because now, like we just said, what if I want to turn through an angle of pi over 3? I could do it then. So cosine pi over 3 plus I sine pi over 3. What's cosine pi over 3?
1/2
Good. Plus
root 3 over 2.
root 3 over 2. That is exactly, if you rotate through pi over 3, you start it here and you're trying to go to here, you end up at this, 1/2 plus rad 3 over 2i. It's not really drawn to scale, but it will.
So that's just a completely different dimension though? Like,
Yes, and it's a physical dimension. They're not made up. The word imaginary, we could have called normal negative numbers imaginary, because people were when they were first thought up.
When they were first solving like quadratic equations, they didn't even
Yes.
factor in the negative because it didn't exist at that
Yes,
point.
and they even rewrote, if you had 3 minus 4 equals x, they would rewrite this as 3 equals x plus 4. They did not like the idea of a minus. They just rewrote everything in terms of plus.
did he just prove like the back rooms is real?
The what now? What are you? Alright, what's up?
Isn't there like imaginary numbers and like to explain electromagnetism too?
Oh, shit, yeah.
It pops up
Um,
in Heisenberg's uncertainty principle.
You have electromagnetic waves.
Yeah.
So the magnetic waves are always perpendicular to the electrical waves.
Yeah.
So you've got, when you do the math, the real part of your work is the electrical part, and the imaginary stuff is related to the magnetic field.
Because because I is perpendicular to the
Total.
axis you're on.
I is always perpendicular to the axis of movement along which your electrical field is going. So that's a little bit more, let's not go there. Okay. So, I want to do a little more with this guy. Do something more concrete with him. Let me see, where is it at here? So we got this. Right? Let's write a few terms of this. Write a few terms of this. So if n is 0, what do I get? This is all going to be minus, but if n is 1,
Negative x over 5.
yeah, so if n is 1, I'll get negative, well, I'll get minus 1/5, right? Yes, hello. Minus 1/25, right, because it'd be negative 1/5. If n is 1, this will be x over 5. What am I doing? Oh, yeah, okay. All right, let me reset. It's been a long day. Okay. Everybody with me so far? Please, yes, please double check it. And if n is 2, I get x squared over 25 times negative 1/5. It's negative x squared over 125, right? And then I keep going. Now, if I integrate this, right? This side I'm gonna get this. Integrate this, what do I get?
Negative 1 to x.
Good?
Negative x squared over 50.
Good?
Negative x cubed over
3 times
3 times 125. Which is like 750, right?
The 3 times 125?
Now let's double check.
370? Yeah.
When we integrated the series form, right? And again, is everybody, we'll do some more of this, we'll do some more, but all we did, this was just integrate x to the end. That's the definition of the integral of a power. That's the first thing you learn when you do integration. X to the n plus 1 over n plus, kick ass. It's that simple, it's that straightforward. Let's see, what are these terms? So let's write this down. So I got negative 1/5 sum x to the n plus 1 over 5 to the n plus 1. So let's see what we get for terms here. What if n is, oh, this is n equals 0. What if n is 0, what do we get?
X
X.
over 0.
Negative x over 5.
Negative x widths.
X, 5 to the n, 5 to the 1 times 0, it's undefined,
Because
isn't
5 to
it?
the 0 is 1. 0 plus 1 is 1.
Oh, 1.
So it's 1 on the bottom. Here we go, guys.
Wow.
And x to the first, so you get this, right? n equals 1. What do you get? 1/5 times x squared.
10.
5 squared times 2.
Isn't that for n equals 1? So 5.
Yeah, we are doing 1. We're doing 1
5
right now.
times-
So
5
n
times
equals
2.
0 is this.
Yeah.
Yes. n equals 1 would be x squared. Oh, I'm sorry, yeah. 5 to the first is 5.
Times 10.
Times 2. 10. So this is negative x squared over 50,
Yeah.
right? You can see what I'm saying?
Mm-hmm.
So you can differentiate the power series directly, the summation form, and it's relatively easy to do. You can differentiate it, you can integrate it. If you have time and you want to check yourself, do a few terms, right? And then check it against what this says you should get. Does that make sense? So we integrated this, and we got this. Well, let me check it against the terms. Let me make sure, because integrating a polynomial is easy as shit, right? Maybe. So then you can kind of compare it to what your power series representation says you should get, and see if you actually get those.
12 plus 75 times 5 is 375.
Maybe? No?
Awesome.
Yeah, because then when you do it for x or n equals 2, you get 75 on the bottom times the negative 1/5. Because it's 5 squared, 25
Yeah,
times
yeah,
3
yeah.
is 75, 370. Okay.
Alright, so that's one thing right there. So, anytime so for example, let's do this is kind of nifty. I'm gonna erase all this, you guys ready? Sine x is one we do. Let's do this real quick. Let's kind of review how to do Taylor series with cosine. Then I'll do the next thing I want to do with comparing sine and cosine. So what's the process for creating a Taylor series? So if I want a Taylor series, the really cool thing about it, I think I showed you this last time. If I wanted to make a Taylor series for f of x around x equals a, right?
Start by taking the derivative.
Say it.
Well, first of all, you would plug
Yeah,
in.
let's write what it looks like first.
Okay.
So I'm gonna take n derivatives evaluated at a over n factorial times x minus a.
to the end.
Now, we developed that form last time. We developed it, and now I just want to point out again the thing I said at the end of class. I think, or towards the end, it's the nth derivative, n factorial, nth power. I mean, come on, that's too good. Pretty simple to remember.
Oh, and the ends are actually the same thing.
There you go. Okay, maybe. Okay, so, in fact, let's see. Well, I'll work on that. We'll do that on the fly. So for cosine, what I want to do is I want to develop. So let's kind of write the terms of this out. If n is 0, this will be.
First term will be cosine x.
Well, let's just do it for this.
Oh.
Right? If n is 0, it's the not derivative. It's not a derivative at all. 0 factorial is 1. X minus a to the 0 is 1. Plus, if n is 1, it's the first derivative of a divided by 1 factorial times x minus a to the first. Plus the second derivative over 2 factorial x minus a squared, and so forth. It's kind of crazy. We developed this formula last time together. We created it. So now it's just a matter of how do you remember what the parts are? How do you remember what it looks like? Once you've got that, now how do you construct what you need? So can somebody tell me, in this expression, what is Cn? It's a power series, right? Taylor series is a specific type of power series where the Cn's are created.
It's everything on the left.
F of A.
Yes, basically everything can just
Yeah,
go there.
ev-
So this is C. Cn. So we're just, this is what I said last time. If I want to create a power series, I can just make up a Cn. I can say Cn is n times n plus 1 over n factorial. Have fun, right? Taylor series is creating a power series where the Cn's do a lot of work. They make things match. They're the things that are making the polynomial values eventually match the function values. Maybe. So, what's a kind of a nice, organized way to do this? Let's see. So I need to know what. So here's f of x is cosine x. What's f prime?
Negative sin x.
F double prime,
Negative cosine x.
triple prime,
Sin x.
and so and then of course f 4x. We officially cycle back, right? I like it. So what is f of, oh, we're gonna do a Maclaurin, let's say Maclaurin. I always forget how to spell Maclaurin, something like that. Is it A? Okay. Wanna do it around 0 then, right, for Maclaurin? Yes.
So as far as like, problems and stuff like this, we would be trying to like find out at which derivative are we getting a close enough approximation to like the function that we want.
No, okay. We have to construct the entire series.
Okay.
Right, some problems might say, come up with the first 5, or make T5. If they say make T5, that just means the first 5 elements of the Taylor, making a polynomial, right? So if you look at the handout, I first start with the polynomial, and then I talk about the series.
Okay.
Right, so the polynomial can stop at some point. So a problem could say, figure out T5, which means just take the first 5 terms of this. So you just focus on doing that, right? Is that all right?
Yeah.
Okay. If x is 0, what is f of 0? 1. F prime is 0. 0. Negative 1. 0. 1. Okay. So sine and cosine are kind of boring, but they're kind of nice, kind of step into this stuff. Not too much happening. They're relatively nice, well-behaved functions. Okay. So if I want to put all this together, let's start writing out some elements. Oh no. Poor little dude. So let's see. F of A. So f of 0 is 1. So cosine x equals 1. What happens in this term?
It just goes to 0, so it's 1.
Good. So the next term is going to be here. So it's going to be minus 1 over 2 x squared. So everybody, now I'm just throwing stuff in. So get your function, take the derivatives, evaluate at the number that you're building it around. Right, so if it's a Maclaurin series, you're building it around 0. What does it mean to build it around 0? What does that even mean? What does that mean?
Like A with 0?
Yeah, set equal to 0, but what's it mean in a broader sense? If I want this to work, I mean, it might have an interval of convergence that's infinite, but most often, when is the approximation going to be good? When I'm close to what I'm building it around. When is this going to match exactly? It's going to match exactly at 0, right? Because at 0, aren't all of these going to be 0? So, and that's exactly what it is at 0? Yes.
So for different functions, would it be more accurate to build them around values that weren't 0, depending on what the function is?
Yeah, for example, if I had natural log of x, do I want to build that around 0?
No, you would build it
Because
around
natural log of 0 is
undefined.
undefined, right? So depending on the function, there might be certain values that are out of bounds. You can't even build. That's why very often we'll build for natural log of x plus 1. We'll make a Taylor of Maclaurin for that. Yeah. If I keep going, so that's the first, no second, third, no fourth. Sorry. Yeah, first, no second term. There is a third term. No fourth term. There is a fifth term. Right.
So then the negative 1/2 x squared, that's our third term, right?
Yes, I like it.
So then y is an x cubed.
Because the first term is x to the 0.
I got
Yeah,
you.
okay. I like it. So let me say it this way. 0 derivative, first derivative, second derivative, third derivative, fourth derivative. So fourth derivative, that's going to be 1 over, what's going to be on the bottom? 4 factorial, which is 4 times 3 times 2? 24. X to the 4th. Dot, dot, dot. Right? Maybe.
And then it's gonna be 1/20.
And
Oh,
then would E of, oh wait,
Or, yeah, on the, if we were to do something like the 5th, does it just then come back to 0? Like if you were to take x to the 5th, or f to the 5th?
yeah, because we'd be back
Oh.
at negative.
Yeah, we'd be
Yeah,
back
yeah.
we'd be back at negative sign, so it's back at 0 again,
back
it
to 0.
just
So
starts
every
repeating
other
again.
one is 0, of course. Right?
Mhm.
Okay. I'm not worried about. Let's see.
So we wouldn't have a value for any function of, we wouldn't have a value for x for anything raised to an odd power, I should say, right?
Yeah.
Except 1.
Yeah.
For
Yeah,
the
yeah.
one
Zero.
derivative.
And because it's
Yeah,
a Maclaurin series.
for the
A is
derivative.
0.
Yes. Yes. So all a Maclaurin series is, it's a Taylor series where A is 0.
Okay.
But the only reason we gave it a different name is because we wanted to give Maclaurin props. Right? In fact, if I just write it like this, let me just write it like this. This is a little better, so let me do this. Now we can see how to write it this form, right? This would be sum n equals 0. Let's see if we can do it. We can write it in that form. It's even powers on the x, correct? Let's start there. Even powers on the x.
So 2n.
Yeah. Is that cool? Yeah. So yeah, I really need you to realize this is the first term of cosine, yes, of the series. This is the second term. This is the third term. This is what we ended up with, right? Why am I saying that? Because I really want this done. This was 0, so it didn't even get factored in creating the series, correct? But this is the series. This is the series I'm working with. It's the first term of the series, 1. Second term is this, okay?
2n factorial?
Yeah, let's check it out. If it's 2n factorial,
At 0 it would be 1.
0 would be 1. At 1 it's 2 factorial.
At 2.
At 2 it's 4 factorial. It's good.
Looks
Right.
good.
And then of course, -1 to the, should it be this? Or should it be +1?
Plus 1.
Well, the first term is,
Yeah, plus 1 because the first term is.
well, the first term is positive,
So just that.
just that.
That's
Yep.
Okay, I like it. Okay, maybe. Okay,
And that's our series, right?
yes, this is your Taylor series for cosine.
This is just like 11.9, you're just building a series.
Yeah, 11.9 was just general power series, so we didn't build them, they were given to us. Taylor series is the first example of us building something. It ends up in the form of a power series, but we're building it with a specific intent.
Okay.
Okay. Okay. Yeah, so now, okay. I'm gonna erase all this. I'm gonna put up here. Let's do this. Yeah. All right, you guys got all you need, hopefully. So let me write a couple, well, let's put sine up here. Sine x equals, and this was basically the analog to cosine. Together they kind of fill each other in. That was what, and the whole e to the ix thing kind of shows you how they fill each other in. So this will be x minus 3 factorial plus x to the 5 factorial. Dot, dot, dot. Right? And this will be equal to, so what is this in general? Actually, we can make it
2n plus 1.
yeah, x to the 2n plus 1, if I make the 0, there we go, over, right, x to the 2n plus 1, so I get odd numbers up here. Is that cool? So 2n even, 2n plus 1 odd. Might have to be 2n minus 1, depends on the situation. Either one of those could be an odd. Over, of course, the nice thing is these match, so whatever this is, this is.
And then is it
The negative.
negative -1 to the
Oh yeah,
n plus 1?
-1, and that'll have to be,
N plus 1?
well, no,
It's still negative
Or
1 to
it's-
the end.
still
It's
is.
negative, okay.
Yep. Because we're starting at 0. Now, all right, let me do this. There's so many different parts to this. Let's do this right now with this, and then I'll do what I wanted to do originally. If I wanted to rewrite this, starting at 1, can I? Am I allowed to? There's 2 ways to do it. All right, I really want you guys with me. All of this is important, but it's all kind of like connected and not connected. I could just take the first element off. I could just put a 0 in, take the first element. That's not what I want to do. I want to make the whole series start at 1 instead. Yes?
Could you then just do, negative 1 to the n plus 1, x to the 2n over 2n plus
So we wanna subtract one?
or yeah, subtract 1, x to the 2n.
Minus.
Don't we
Over.
just 2n minus 1 factorial?
Yeah. Okay, so you can adjust. This will become important at some point in your studies. Being able to adjust the index. Because you might need to add two series together, which is what I thought they were trying to do a little early. But you might have to adjust one guy's index so that they become like terms. I don't know if that makes any sense. Why would I need to do this? Somebody out there is like, why is he doing that? I'm just doing this to show you that I can. Is there a reason right now to do this? Nope. I just can if I wanted to, and I don't want to, so I'm gonna erase it. But you can change what this starts at. You just have to you have to change what these are, of course. That only makes sense. Yes.
So power on the negative. Is that right, the power on the negative? Or should that also be negative? Minus
No,
one?
it could be -1 or +1, to be honest. I mean, the funny thing about this,
Oh, right.
would this be wrong? +10? Nope. Nope. We just normally like to stick around and, yeah, so. Okay, so you could have made this a -1 if you like. That's symmetry. I like it. Okay. Is everybody with me? The only thing that does is it offsets which, does it start negative or does it start positive? That's all it does, right? Okay. So let me erase that. I'm gonna freak you out with that, I'm sorry. So you can do that with any series sitting anywhere. Do that. Now, take the derivative. What's the derivative of sine? Holy shit. What's the derivative of x? 1. What's the derivative of this? 3x squared, right, over 3 factorial, right? You with me? Plus, same thing here, right?
So you can write that as the derivative. Can you write that as n minus r?
Just hang out with me. Stay with me. Is that all right so far? You guys with me? Now, this is not surprising. We already know what cosine x is. We just developed it, didn't we? Didn't we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial? Isn't that what we just got? Right? Okay, now take the derivative of this.
Two n.
Plus 1 x.
Yeah, it'll be 2n plus 1 comes down, right? X to the 2n plus 1 minus 1, so just be 2n, isn't that cool? Over, and this is just a constant, yes? This is just constants. X is the only thing I'm taking derivative with respect to, yes? So what happens here, let's see. This will become, you see what happens here?
Yeah, you can cancel and you get 2n.
You can write this like this, right? Bam, bam, we've done that enough. I think you guys are cool with that, yes, maybe? So you'll get -1 to the n, x to the 2n, over 2n factorial. Do I need to change this? If n is 0, what do I get?
1 over 1, so no, you don't need to change it, right?
If n is 0, yeah, I'll get 1 over 1, and that's where
It starts.
cosine starts. So sometimes you have to, sometimes you don't. That's the point I'm trying to make. But also, so there are several things I wanted to accomplish there. One more thing that I even thought of in the original beginning was talking about changing the index. You could do that. Yeah.
I was just gonna say, because you took the derivative of the series, doesn't n have to become 1?
In this case, no, because n equals 0 does give me this.
Okay.
So that's not like a firm rule?
No, it isn't. In fact, I think I tried to say that before, and I wanted to make sure you understood. This is why I left the index blank when we did the integral, because you need to look at what you get. So watch this. If I take the derivative of this, don't I lose a term?
Yeah.
Why didn't I lose a term here? Because the first term was a variable.
Oh, okay.
So you actually end up with the same number of, I know there's an infinite number of things, yes? But does everybody understand what I mean? The same number of? I didn't lose one? Okay, maybe. So you just don't know until you get to there, then you stop and you say, if I let n be 0 still, will it give me something that shouldn't exist? That actually happened to us last time. I don't know if you guys remember that. Can't remember what the problem was, but okay, maybe. So realize that integrating and differentiating things in this form is very freaking easy. It is crazy easy. The only new thing to be careful about is, does that have to change? Yeah.
So can n be any number?
Yes.
As long as it's not real? Yeah.
As long as the values of it give you what's supposed to. So I can make n equal negative 17 billion as long as I change these to make the right things come out. It's just shifting stuff, yes?
Okay.
Yeah, okay.
That wasn't an 18.
What?
You said 17
I
billion.
know, exactly. I'm trying to do things out.
Variety
Glad somebody
of
noticed.
places.
Because the indices is just where you're basically deciding to start the series.
Say again, sorry?
The index is where you're just deciding to start
It's not
looking
a
at the
decision.
series.
It's not really a decision.
Okay.
This has to be a certain value to make sure you get the right outputs. Yeah.
So if you want to like summarize the process, you'd say like use like that nth derivative formula to like build a sequence and then try to recognize that and build a power series off of
There were several things happening up here.
Yeah.
I could just give you a series and say, take the derivative of the series.
it. Okay.
And it doesn't have the elements here, right? You know, I would just give you this and say, take this guy's derivative.
I got you.
Does that make sense?
Yeah.
Okay. Or I could do a problem like this, which is normally the better way to go, just to kind of keep tabs on what's going on, right? Okay. Let me see. Okay. All right, this might be good to do. So here's cosine, right? Here's good old cosine. Let's take a derivative of it real quick. Right? You guys with me? What's the derivative of cosine?
Negative sin.
Bullshit. Derivative of this.
Zero.
Derivative of this.
2x over 2x.
Yeah, so it'd be minus 2x over 2 times 1, so it's minus x, right? And this will be plus
X cubed over 3 factorial.
3 factorial, right?
It's just the.
Yeah, I'm just looking up there.
Yeah.
Just signs.
It's just the negative of this, yes? Which makes sense because it's supposed to be negative sign. But let's see what we get when we attack this directly. So I'll leave this alone for now. This comes for the ride a bit. Check it out in a minute. What happens here?
2n minus 1.
2 in factorial.
So this one I can do 2n times
2n minus 1.
factorial, so these cancel, right? The same thing we've done several times. You notice something different? So if I let n start at 0, what happens?
No.
Negative power.
Right? Am I supposed to have a 1 over x here? In fact, this might be exactly what it was. Do you guys see that? So, all right, let me stop for a second. Do we know what we're supposed to get? Isn't that supposed to start at negative x? If I start at 0, does that make sense? When I put a 0 in, what do I get? X to the negative 1. Am I supposed to have a 1 over x?
No.
Nope.
It also wouldn't be negative.
Yeah, exactly. It would be negative 1 factorial, which you can do, but for right now, we just don't know what it is. There's a larger idea that factorial fits into, but we're not going to talk about that right now, okay? But yeah, just for right now, you can't get a negative in a factorial for us. Yeah, so that's an immediate red flag. You guys with me? So I have to start at 1, but now isn't that, all right. Is everybody semi with me what's happening? So taking the derivative of a series is easy. It's actually easy. The one thing you gotta be careful about is the index. Does this look the same thing as what we said science was before?
It's like.
And actually, yeah, this matches out, right? Let's see, what is happening? Something's a little different. Let me see. Oh, okay. Oh, there. Yeah, that's right. Okay, I'm overthinking. How can I make this look more like that? If I wanna make this start at 0. This is kinda nice, I like this. I wanna make it start at 0. When I plug a 1 in, I get a 1 up here, yes? Now when I plug a 0 in, I wanna get a 1 up there. So what's that gotta become, of course?
Plus
1 plus 1, right? So I want you to understand why that's legal. My inputs have changed. So to have the same outputs, this has to change, yes? It really is just a shift.
Can you think about it, just like plugging in n plus 1 for n?
Yes,
So that
yes,
you
exactly.
multiply
You can plug in n plus 1 for n, exactly. So this would be -1 to the,
N plus 1.
and we'll talk about that in a minute. On the bottom, of course, I get 2n plus 1. Factorial for the same reason. Why is that not the same?
Because
This
it's
is
the
a really
neg-
easy,
It's the negative.
because it's the negative sign. Yeah, so of course I got one more negative. Does that make sense? Okay, so that was a lot of things all at the same time. We took a derivative, we figured out what the index had to be, and then we said, I don't like that. Let's make it like a 0 like it's supposed to be.
But it's fine if the index is 1.
Technically, it's fine. If the only question was take the derivative of this series,
And
and you do this, and you stay here, you're fine. There's nothing better about this, to be honest. I really want that to make sense. It's only if you were in a class where you're trying to combine power series, so you had to have like terms. I really want this to make sense. If I had to combine this with this, are these like terms? Nope. You guys see that? So then I could try to adjust the indices to make them like terms. That would be the next level of this, yes?
So now, if we're asked to like integrate e to the x squared,
Yes.
what we would first do is we'd find its Taylor polynomial and then integrate that.
Let's do it.
Okay.
Oh, boy. Okay. Love it. I'm gonna erase all this purple and green. Okay. Real quick, let's do this. E to the x, if I wanna build a Maclaurin series for it, right? Can you guys do the first couple steps in the direction of building this Maclaurin series? The Maclaurin means A is 0. I know I want. As well, this one, I'm gonna put it general. So for Maclaurin, Taylor, Lauren, same damn thing. I don't know if you guys remember Rolle's theorem, mean value theorem.
It's been a while.
Okay, I won't go there.
A is 0 in this case?
Yeah, we're doing a Maclaurin series. Yeah.
Right.
This one's like pretty. You just say e to the x would be easier, right?
Yeah, we'll do one more thing with this. I like it. We'll do one more thing with this than we did before.
How close is that?
My cheese.
So this one's pretty boring, yes? Kind of? I mean, what is this? Can't you just tell me what this is?
E to the x.
Spamming you.
Yeah. Exactly. Why am I not doing e to the x squared? Because I don't want to. Holy shit. Can you imagine doing those derivatives? It would very quickly become product rule, and then there'd be multiple product rules, and there'd be too many product rules, and you slowly go insane. Or more insane, I should say. But is that cool? I mean, e to the x is just your buddy. It's a nice little dude, right? So what is f n 0?
1.
1. This is kind of cool. So every single top is 1. Right? So we can actually write this immediately. This would just be 1. This would just be x to the n over n factorial. Right? That's what e to the x comes out to be. Are you guys okay up there? Now, we are going to do, well, of course I'm running out of time, which is kind of funny, but We're gonna do, I think, non-Maclaurin building of a function that's a little bit grosser than like e to the x and cosine x, right? We'll do one more example so you can really see what the steps are. Here, the steps are done at the beginning. Is everybody cool with that? So every derivative at 0 is 1, because every function is, every derivative at 0 is e to the x, so that's easy. So that's e to the x. What's e to the x squared?
You just plug in an x squared where x is.
Yeah. So it'd be x to the 2n. So what's the integral? Oh, actually, before I do that, can you find the interval of convergence for this?
For e to the x? For e to the x.
E to the x squared. Can you find the interval of convergence? Not just can you. Do it. You'll sit there and go, yes, I can. And just stare at me. So any Taylor series we create, or Maclaurin, it's just the power series. I can ask you all kinds of power series questions. It's a little weird, but it's alright. It'll be okay.
I got all numbers.
I got one.
Yeah, exactly. Thankfully,
I'm glad
this
you
x
said it
squared
first.
doesn't mess anything up, right? So this equals 0, which is always less than 1. Okay. So this works for any numbers you want to plug in. Any value of x you put in, this will actually converge to this. The further from 0 they are, the more terms you might need to make a better approximation, yes? We had a very concrete example of that last time, where I had like a 10 was the answer, and it was slowly getting there. We had to go forever. I don't know if you guys remember that.
E to the 10 billion.
I can't remember. So if I want to integrate this now, isn't it relatively simple? Yes? Maybe?
Oh.
Yes?
I'm confused because y was squared is an e. I mean, x squared.
Oh, because the question was integrate e to the x squared using a Maclaurin, yeah. Using a Taylor series, yeah, or Maclaurin series. Is that cool? That was the question, so we kind of built our way up to it.
We pull one over and factorial out of the integral.
But you can't pull it out of the summation. Because
It's
n,
control of a factorial. Oh, you don't
See
have
what
to.
I'm saying?
Oh, yeah.
X
Okay.
to
So
the
we can't
2n
move the
plus
integral
1.
in then, and then pull the.
well, integrating a sum is just integrating. I really want you guys to understand. What's the integral of x plus x squared minus 2? Is this hard?
No.
Can't
Extremely.
you just integrate each term? Yes.
Sorry.
You have to bring the integral into each
It's
term.
like
Alright,
effectively a
so how do we integrate a sum of a bunch of terms? I integrate each term.
Yeah.
What does each term look like? This. So you don't bring the integral in. It's the fact that this is a sum that allows you to integrate each term. Does that make?
Yeah, I'm just trying to get rid of the n factor.
Oh,
It's a constant.
it's just a
Yeah,
constant.
yeah, yeah.
It's a constant according to this guy.
Yeah, yeah.
I need it to still be a series at the end, right?
Mhm.
So I'm gonna get the sum. What do I end up with? X to the
2n
Or
plus
2n
1
plus
2n plus 1.
divided by 2n plus 1 times n factorial.
And let's see if this still makes sense. N equals 0. Still makes sense because if I look at, I should have written some terms out. Some terms of this, when n is 0, I get 1. plus x over 1, blah, 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 blah. So when I integrate this, I'm going to get x. So when n is 0, I get x over, so if you want, yeah, sorry.
Why? is
Plus
this
c,
not-
sorry.
Oh, okay.
Yeah.
Why do you not need this?
Yeah. So they would have to give me more information now to figure out what c is.
Right.
Yeah, which is actually doable.
Would this be a constant that you're adding to figure, to like get to that point where that would be true?
Yeah, they'd have to give me, so back when we first did integrals, what information did they have to give me? So if I had integral x dx, and I get 1/2 x squared plus c, what else did they have to tell me for me to figure out what c was?
The value on x is 0.
So again,
The value on x is 0.
well, yeah, so this is my f prime, and this is my f, right? So I'd have to know what f is at some value. Could be any value. They'd have to give me a point, basically, right? So they have to tell me like, f of 1 is 3. Then I can plug a 1 in and make this become 3 to solve for c. Right. Okay. Maybe. So they'd have to give me more information to figure out what that c is. I think they actually have. Yeah, well, okay. If you want to, yeah, here we go, beautiful, this is exactly what I want. Beautiful. Now, let's do this. That's an indefinite integral. What if I wanted to know the integral from 0 to 1 of e to the x squared? Right? What I do, well, I know the answer to this is that. And the question would have to tell me, so let's say correct to within 0.01. Let's see what happens here. What is the integral of e to the x squared? It's that thing, right? Okay, so what is, let's write some terms out. When n is 0, I get, I just get x. Is that cool? And the plus c, of course, is definite integral, so the plus c is gone. So I get x plus, and in fact, we can just look at this guy. What else? What do I get next? I get x when n is 1.
X when n is 1, x to the third.
X to the third over
6,
over
18.
3 times 1 factorial, right? So that's just 3.
Oh,
Right. Plus, when n is 2,
X to the
the
fifth.
fifth over
10.
2 times 2 is 4 plus 1 is 5 times 2 factorial, so 5 times 2, 10, 11. Let's see what we got so far. Right? So when I integrate this, so I want to evaluate this from 0 to 1. What's nice about 0? Makes them all 0. What do I get when I put a 1 in?
1 plus 1/3.
1 plus 1/3 plus 1/10, right? Do you see how this is changing by 0.1? So I might want to go one more step out to be within 0.01. So you can just pick as many elements of the series as you need. So I really want this to make sense. I can't get the exact answer to a definite integral of e to the x squared by hand. I can't, because I would have to go to infinity, right? It would take a while to get my kids to do it, and their kids have to keep going, their kids have to keep going. So what I do is, it's sort of like that Newton's method. Remember Newton's method? Anybody? No? You just kind of kept going until that stopped changing in a certain decimal place.
Yeah.
So what's one more, let's see, what's one more element in this?
X to the
0, 1, 2, 3. So So x to the 7th over
7 times 3 factorial.
7 times 3 factorial, which is 42?
7
Yes.
times.
7.
42? 1, 2, 3, yeah. 3, 6, 7, 8, okay. And that would be 1 over 42, which is like 0.02 roughly, right? So we're getting pretty close. But do you get the idea of how you could do this? I cannot get this definite interval exact by hand. I can't. But at least I can do something. In fact, most applications just require us to be correct to maybe at most 6 decimal places, right? It depends on the application. If you're talking about gravitational waves, you might have to be correct out to the 40th decimal place. But then you just go freaking further out. Who gives a shit?
You just do computer. Have a computer.
Yeah, at that point you do the computers, of course. Yeah. But humans have to know what the hell to program the computer, right? And maybe. So integrating and differentiating, relatively simple. You just have to be careful about the index. That's one of the most important things to be careful about. Let me see. I kind of wanted to, everybody still has this handout here. It had 11.8 on one side, 11.10 on the other side.
Thank you.
Oh, yeah. Oh, that's on the, that's right. Just have to find the place. So guess what I'm gonna do? Sorry. I kind of wanted to either do a few of the problems on here, or just do some other things. So there is one thing I want to do right now. Let's see if you guys. I want to construct a Maclaurin series. Let's say for and I want you to do it very quickly. So I'm not going to make you memorize the table on page 768, I think it is. Yes, 768. It's a really good table in the book. It's the table of all the functions that we currently know in this class that work and have Taylor polynomials that actually agree with the function. Okay. So I would give that to you. But I want you to construct this guy. But I want you to do it quickly using that table. Right? So the table has stuff like e to the x, sine x, cosine x. If I know cosine x, can I just square it somehow? Do you want to do that? Can you imagine trying to do that?
That's where I'm.
You kind of with me? Isn't cosine x 1 plus, let's see if I remember, 1 minus x, oh Jesus.
Isn't cosine squared
X
x
squared over
minus sine squared x
2
1?
plus x to the 4th over 4 factorial, right? If you multiply this by itself, you understand that's an infinite foiling. In fact, that's an infinite foiling. Do you understand what I'm saying?
Yeah.
You could actually multiply this. Do you want to do that?
No.
I don't like it.
Does anybody have a suggestion on something to do with this?
Rewrite cosine squared in terms of sine squared.
Nah, that would make it like a little bit better. Still sucks.
Root it and use a
Howard
Howard.
But that's what we're saying. If I square this, that means I would have to FOIL this infinite polynomial out.
Square root the whole
I
thing.
don't feel like doing that. So what's getting me a little down, not too much, because I'm sure it's been a while. Trig identity, anybody? Trig identity?
I thought that was just one.
Half angle.
No, that was a plus, guys.
Half angle.
Then it's 1. That would be the ultimate troll.
If you do that on a test, I will cry because I'm not gonna know. I'm gonna see that and I'm gonna think.
No.
I'll give him ideas.
Anyone know what this is?
Cosine of 2x.
Oh,
Oh,
Okay. All right. What is cosine x? Cosine x is that business over there, right? Which is the sum of x to the 2n over 2n factorial with the negative 1 doing stuff. Yeah. So this was what you would have. So how do I get this? Cosine 2x. I would just put a 2x in it, right? Do you guys see that?
Yeah.
But I will give you, again, what is something you're supposed to know coming into this class?
Trig.
Trig. Not only like cosine of 30 degrees, but you should also know identities, right? Yes?
So for there, we just drop in like a 2 constant? and we get-
Yeah. Now you just have to throw in negative 1 to the n, 2x to the n, over 2n factorial. And you can rewrite that 2 to the n, x to the n, right, if you want to. And that's what it really is. It's almost too nice to believe. So that's why we have certain building block functions that we actually do the whole process. And then once we have them, we can combine them in different ways to make other functions, right? So if you did the whole Taylor series, or in this case, before, for this, did the derivatives, plugged the numbers in, did everything, you would eventually get here someday, right? That's why that table in page 768 is so important, because they're building blocks. I just throw shit in place of x that I need to make almost anything else I want to. Okay.
Are we memorizing those or no?
What do you guys? Yeah. No, you know. I would give it to you on the
On
text.
an exam,
Yeah. Let me see. What do I want to focus on here? Like, look at number 3 on what I gave you. That's kind of like the one we just did. That I think Carmen asked about. Approximate the interval with 3 decimal place accuracy. But be really careful on the test. I would tell you, construct the Taylor series for this using the process, right? Versus use a known series to create this. Are you guys with me? So if I gave you this and I said use the Taylor series process to construct the series, you'd have to get all the derivatives and so forth. You with me? Because I need to check to see if you know this process. And then there's going to be a problem that says, you know, just use it when you already know from the table. And then you just have to plug a 2x in. Okay. You guys see what I'm saying? Is that cool? That's the kind of things. Let me go ahead and give you the practice test here. Before I forget that.
Which is on Wednesday or Monday? Wednesday.
I moved it to Wednesday, so we had tonight to kind of marinate this stuff a little more.
For lunch? Oh. We could just scratch your brain over where it's
Oh, that's right, that's right.
It looks so. I know that in here.
Cotangent. No.
Where are we at?
What do you mean, no?
I mean, no. I feel like I made it pretty simple.
There seems to be a lot of confusion about problems like 2C.
No.
Yeah, exactly.
That's pretty chill. You know, you do the stuff and the stuff cancels and the stuff is good.
Yeah. Yeah.
That's just a ratio.
I'm so happy. Well, if I had taught it like that, would that have been good? Let me see what else gives people trouble. Oh, strangely enough, like 4B, this actually came up last time, I think. It's not already a ratio, but that's fine, right?
You just make
put
it,
the
yeah.
n plus 1 over the n. That's actually easier. You don't have to multiply by the reciprocal or anything. let me see. Number 6 is the one finding Taylor series. The square root one is interesting. And of course, so is the 1 over x. I think that's the one you were asking me about, right, Carmen? Okay.
1 over x.
Yeah. And number 7, this should feel very familiar. Remember we did the linear approximation? And then they said, use your linear approximation to estimate blah, blah, blah. So all Taylor series really are just linear approximations taken to the infinite level. Just cranking the resolution up to infinity, right? I don't know, that might be a good one to try right now, I think.
7?
6B.
6B.
Yeah. Let's see.
What do we do with cotangents again?
Say again?
Cotangents?
What about them?
What do we do with them?
What do you do with them? You look at them, you simplify them, I don't know.
That's not a good thing.
I-
That is a
That's an art campus.
No, 2A.
2A.
Oh.
1 over 10.
I think that just diverges, low key.
Alright, so let's look at 6B.
I think that diverges low key.
Real talk.
Okay. This is pretty good because we haven't done a lot of non-Maclaurin stuff yet together. So this one is just a pure Taylor series. A is not 0. So what are the steps? What do I need to do first?
Take some derivative.
Take some derivatives, I like it. So my function is 1 over x. What's my first derivative?
Maybe negative 1 over x squared. And positive 1 over x to the full third. Positive negative, positive 2 over.
Yes. Next to -2, right? So -2 comes down.
Yeah.
Cancel that negative, and then power goes down by 1.
The third, yeah.
Are we cool with the fact they just said down by 1 and then made it 3, right?
Yeah.
Okay. So it kind of keeps going like that. So, do you already notice something about the numerators involved here? So let's do one more. Yeah, I heard it. Somebody just said it.
And factorial.
Yeah. The top is in factorial. Yes.
How come we're not doing like, for f of x, like 1 over x minus 2 because a equals 2? Oh, okay.
No. So to build this, it's f prime evaluated at a. It's x minus a, yeah.
Yeah.
To the end.
Did Carmen leave for the question that she asked about?
No. This isn't something she asked for.
Oh.
This is something she asked me already.
Oh, okay.
So she's already.
She's chilling. She's
Yeah.
chilling.
Yeah. Let me stop for a minute. The a comes in when I evaluate the derivative, yeah. It's sort of like constructing the slope and then the higher orders of that. So now I want to know what f of a is. A, of course, is 2. So what's f of 2? 1/2. What's f prime of 2?
Minus 1/4.
Minus 1/4.
2 over 8. 2 over 8.
2 over 8. 1/4.
Minus 6 over
16.
Yeah, 16.
3 8.
And then let's do one more.
24 over 32 simplifies to
24 over 32 is something.
8 is that's 3 over
12 over
3
16.
So
over
is there a 3/4?
3/4. Yeah, 3 over 4.
Yeah. Yeah, awesome. And then of course it keeps going forever. Now, real quick. Here's the fundamental question. Now there could be 2 different things I could do. I know in this problem I specifically say find the Taylor series. Right? I could say find the Taylor polynomial. Like if I said find T4. That would be the first 4. Well, T0 would be this, so T4 would be up to the 4th derivative. So then I could just put these in there, figure out what the terms are. I want the Taylor series though. So I actually wanna know what this is. And the mistake that's often made is these numbers kinda come in, no. What is Fn of x? What is the nth derivative of x? What's the pattern here? Well, I can do the -1 to the nth power, is that cool? Take care of that right off the bat. What do we say is the
Would it be n
top?
plus 1? Oh no, because you just make it 0.
Starts, yeah. So pretty cool, what's 0 factorial? What's 1 factorial?
1,
2 factorial?
2.
Okay, so that's definitely factorial, right?
And then it's 2 to the n? No.
No, just here, it'll be x to the n, so yeah, it'll be 2 to
Oh,
the
yeah,
n, yeah. Because we're gonna plug a 2 in, so right now it's x to the n, so what is f n evaluated at 2, which is what I need up here?
Isn't it nice? Is the first time n equals 0 or n equals? That first, the non-derivative.
Yeah, n equals 0.
So then it's
For what?
on the bottom, x to that.
Oh, yeah, thank you, that's right. Because it starts at 2. Yeah, thank you, starts at x to the first, yeah. So it should be x to the n plus 1. Because it starts, when n is 0, this is x to the first. Thank you. So now, this is really kind of nifty. All right. So again, we've done this before. You write down your derivatives, you evaluate them at 2. From here, you could set up the polynomial if I ask for a polynomial, but I'm just asking for the series. I really want this to make sense. This is still important because I could ask you to write some elements out, or I could ask you just for a Taylor polynomial or whatever. But do you see, if you looked at these numbers, can you see the pattern in these numbers as easily? No. Because you've thrown 2 in and you've kind of changed everything a little hard.
Aren't they getting closer to they're getting closer to 1 or -1?
Maybe. And again, this is a finite number of things, so.
Would it be easier to see the pattern if we didn't simplify the fraction?
So again, yes, exactly. If you left the fraction unsimplified, then you can actually see, this was 24 over 32, right? Then you can see the bottom is 2 to the n plus 1, yeah. I like it. But can you imagine more things happening, simplification? Yeah, so sometimes it's just easier to get the idea straight from this. Now, where does this go? This is just a piece of what I need, correct? It would go here. And then I'm gonna divide by n factorial. Do you guys see something that's gonna happen? It's kind of nifty.
The n factorial is gonna cancel.
Yeah, so if I put it together, sum n equals 0 to infinity, I'm gonna put this. And then it's divided by n factorial, so these cancel. And then x minus 2 to the n. So there's the Taylor, let me write it a little better. Sum n equals 0 to infinity over there is the Taylor series for 1 over x. Now personally, most humans would appreciate to see the actual elements, right? If I just glance at this, it's nice, but I don't get a feel for what it does. So what are the elements of the series? It would be 1/2, well, I think it's a little bit tricky because you have to divide by n factorial. Might be easier to just come up there. So it would be, when n is 0, I get, 1/2, x, no, n is 0, that's out. Minus, when n is 1, I get, negative, I get 1 over, 4 times x minus 2 plus 1 over, oh yeah, the n factorial is canceled, so I can't use it. Minus 1/4 plus 1/4 x minus 2 squared, and then I would just keep going forever. So if I wanted to use this to approximate 1 over 1.99, you with me? Why would that make for a good approximation? 1 over 1.99 because we built it around 2. And 1.99 is pretty close, right? Now, before I even do that, what should I do with this? What should I investigate before I start throwing values in for
Interval
x?
convergence.
The radius and the interval of convergence, right? So I should do that work. So again, that's gonna come back into play. So once we can, I don't care where a power series came from, I can ask you to find its interval of convergence. This just happens to be one that we created.
Is that gonna be on this exam, or are we learning that?
What do you mean?
Like, are we gonna find the, ratio of convergence and then make
Have
it
we
to
done
the
with
series around
intervals
it?
of convergence in the homework?
Yeah.
Yeah, so they can show up wherever I want them to, right? So this,
Okay.
yeah, I can do them for any power. I can give you a power series, or I can ask you for the power series you created, right?
Mm-hmm.
Yeah, so, you guys need to see that? Are you guys cool? If I ask you to do the limit, the interval convergence?
We
it
just
would
do it
be
the standard
ratio-
way,
It would
right?
be this
Ratio
limit
test.
as long as it's less
Yeah.
than 1.
Ratio test.
Yeah.
And of course, this would be centered where?
Done it many times.
Of course, it'd be centered at 2. I mean, we know that from the very, very beginning. It's gonna be centered at 2, yeah.
You said the Taylor series doesn't start at 0. How come n is 0 in there?
What do you mean? Sorry.
No, it's not centered at 0.
Yeah, it's not centered at 0. It's centered at 2.
Oh.
Yeah, yeah. And, you know, the standard format for Taylor series is this. From derivatives, is it possible the derivative, the function at the thing I'm interested in can come out to be 0? Yeah, in which case I could make this 1 because the first element, if it's 0, I don't have to include it. Does that make sense?
Mm-hmm.
Okay, but the standard form of series, Taylor series starts at 0. Good. So of course, just like always, I'll have the practice test, answer key on Monday. I've got my office hours. I appreciate everybody who's been coming in for help in the Met Study Center. Those of you who have not been coming in, I understand you might have several jobs like I did going through college. So if you need to, reach out to me for other hours. All you gotta do is ask, right?
Carmen, he just called you spoiled. Because you're always in the
I
math
think
study
that's
center.
enough for tonight. Is that okay?
Mm-hmm.
Okay.
Alright. So next time we'll have a review day,
That's shady.
and the test will be a week from today. I was gonna do a little bit out of chapter 10, but we'll just do that later. I don't think that's a good idea.
What's your favorite color, Carmen?
I prefer not to.
What?
I said, what's your favorite color?
Why are you attacking me?
Sorry, I'm just looking around. I'm like, this is that color, that's that color. I mean, your binder's blue, your phone case is blue, your jacket's blue.
Yeah, but they're different shades.
Your mask is blue, your backpack is blue. I mean,
Maybe she's just accessorizing today. She could have different backpack.
And getting a feedback.